So what we're going to look at now is oxymercuration. And so what this is it's just a way to hydrate double bonds. Okay? And so remember, when we think about hydrating something, we're adding water to it. What we actually see that look like in our molecule is an OH, right? So we're going to add an alcohol across a carbon-carbon double bond. All right, now, one of the things that we want to do when we look at this is think about the role of each of the reagents. And that's one of the things I want to point out is we're going to do this with a double bond. So when we have our molecule, we want to take our attention right to the double bond. So we have one pentene, tell me there's a double bond. And we're going to use mercury acetate and water. And so what happens is the mercury is going to help the water add across the double bond. And what you should put in your notes is that alcohol is always going to add to the more substituted carbon. Okay? So we're always going to see this add to that more substituted carbon. The mercury adds to the least substituted. And then what happens is we add sodium borohydride. And the whole role of that sodium borohydride is just to cleave off that mercury, right? And you get the hydrogen. So our final product is this one here on the end. And we get that 2-pentanol. All right, so the way you would see this, and we can try an extra one together. Is we would write our mercury acetate as step 1. So we would write HgOAc2 with water. And then as step 2, sodium borohydride. All right, this is the first time we've seen these sequential reactions, right, in terms of adding reagents. So what you want to think about here is if there's no numbers, it means you're kind of just throwing them all in together, right? So if any of you cook, it's kind of like a crock pot, you just dump it all in and let it kind of cook. This one means if you were in lab, the direction would say, all right, add your mercury acetate and water, let it stir for some amount of time. And then once that part of the reaction is complete, we add sodium borohydride. So what's happened, the reason we do this stepwise is we want the mercury and the water to completely add across that double bond, right? And get this intermediate, right? With the alcohol and the mercury coming off. Then we don't actually want the mercury in our compound. We want an organic molecule. So the sodium borohydride is a reducing agent. So it's going to cleave off this mercury and replace it with a hydrogen. So that hydrogen that gets added comes from the sodium borohydride. All right. So when you see this, it's always that idea of mercury and water followed by sodium borohydride. All right. Now, what you want to think about is whenever you see this mercury reagent, you're going to add an alcohol to the more substituted. All right. So the other thing you should think about is that there's going to be no rearrangement. All right. So you're going to see no rearrangement with this reaction. So it actually makes it a little bit easier because now when you're looking at this molecule, you're comparing these two carbons that are part of the double bond. You don't have to worry about rearrangement at all. You just draw the product. All right. So go ahead and give this one a try. So if you want, pause the video, draw the major product, and then we'll do it together. All right, let's see how everyone did. So the more substituted carbon is that inside one. So we're going to add an alcohol here. So we'll keep that same zigzag form. And then we add an OH to that group. And that's it. If you want, you can show the hydrogen coming off of here. But since it's the zigzag form, we don't have to show it. All right, so we just add an alcohol to that more substituted. All right, so the two things you should take home from this is first, when you see the mercury, all right, this oxymercuration, it's going to add to the more substituted carbon. And make sure of the double bond, right? We're only comparing the double bond, right? So the two carbons are part of the double bond. And the second part is no rearrangement. All right, so there's no rearrangement. All right, so that makes your life a little bit simpler. All right, the other one we're going to look at is hydroboration. All right, and this is regioselective to the other side, right? It says the least hindered carbon. So this is going to be the first one that adds anti-Markovnikov. All right, so if you remember, Markovnikov is what we just did with the mercury, right? That your non-hydrogen is going to add to the more substituted carbon, and your group that you're adding is going to add to the more substituted. Here, it's going to be the opposite. All right, so let me show you what happens, and then we'll come back to both this regioselectivity and syn addition. All right, so what happens is we add BH3 in the first reaction. So let's take our double bond, and let me show you what it would look like in a reaction scheme. So what we would have in step 1, right, is BH3. And then step 2 is going to be sodium hydroxide and peroxide. Okay. So when you look at this in a reaction scheme that I would give you, it's going to look something like this. So step 1, we add BH3. You're going to add one of the hydrogens as the double bond pushes into those electrons. So boron actually has an empty p orbital, right? Or it's a Lewis acid is the other way to think about it. So it can actually accept these electrons. So these electrons are going to push into that boron. And at the same time, it's going to donate these hydrogens, right? So it's going to donate one of the hydrogens as the electrons push up. And that's why we make these two new bonds. All right, so different than mercury, when we did the mercury reaction, we added that alcohol in the first step to that more substituted carbon, right? So we added that alcohol here in step 1 and had the mercury. Here we've done it reverse, right? We've added the hydrogen first to that more substituted carbon, and we've put the boron on that least substituted carbon. Okay? So we're talking about Markovnikov's rule. We've actually put the boron on the least substituted, so we're adding anti-Markovnikov. Right, the other thing, the syn addition, just means you're adding to the same side. So the hydrogen and the boron are actually on the same face of that double bond. All right, so again, we don't want a boron, we actually want an alcohol. So then this reaction can go 3 times. So if it had a BH3, you could add the second hydrogen and then the third hydrogen. And so you could actually have 3 of these organic molecules attached to the boron. All doing the same thing, it's just it can do it 3 times. Now, the whole point of adding this group here, the sodium hydroxide and peroxide, is to swap out. So we're going to use that NaOH and peroxide to switch this to an alcohol. Okay? And so the whole point of this group here is to do this conversion and convert it to an alcohol. All right, so if we look at the top one, we know that the only 2 carbons we care about are those 2. And in this case, we're going to add anti-Markovnikov, right? So mercury added to the more substituted. When you see boron, you're actually going to add an alcohol to that least substituted. Right? And so if I highlight those 2 carbons, that's where it was. Again, the other thing I'd write about this is no rearrangement. All right, so it's really nice that you don't have any rearrangement. So with acid and water, you have to watch out for rearrangement. Mercury and borohydration, you don't. All right, so let's try a few. All right, so here's a review of just different ways to put alcohols on the molecule. All right, so go ahead, give this a try, pause the video, and then we'll do it together. All right, let's see how everyone did. So where I would start is you want to see the functional group. Right? So we have a double bond. So there's a double bond right in the middle of the molecule. And then what's my reagent? So I see BH3 and sodium hydroxide and peroxide. I should know that anytime I see sodium BH3, sodium hydroxide and peroxide, I'm always going to add an alcohol, so an OH, to the least substituted, right? And that least substituted carbon that all on. So I'm only comparing these 2 carbons. And since I know that BH3 followed by peroxide is going to add an alcohol to the least substituted, I know it has to add in that carbon. All right, so let's start off by just drawing the molecule exactly the way it is there without the double bond. So we'll draw that. Those were my 2 carbons with the double bond. And we said that when it's BH3, we're going to add to the least substituted, right? Remember, that's the carbon that's attached to the least amount of carbons. So this one's attached to 1, 2. This one's attached to 1, 2, 3. So it goes on this one to the right. So then we put my group and we get my OH. Right? And we do get some other salts and stuff going on, but we really just care about the organic product. Right? So this is all you'd have to draw. Right? And then again, we're losing the double bond on all of these reactions. All right, the next one, which jump out at you, is the mercury. All right, when you see mercury, we know that we're going to add across the double bond. But in this case, when it's mercury, we're going to add to the more substituted carbon. All right, no rearrangement, and we always add to the more substituted. All right, so we'll draw our molecule just the way it is, like we did above, but without the double bond, and then we put our OH. Okay. And I know in the previous slides, I drew that intermediate either with the mercury salt or with the BH3 coming off, but that was just to show you how the reaction proceeds. This is our major product. All right, so one of the things now that you're getting is not only can we put an alcohol in a molecule, but we're starting to have this toolkit of reagents that let us decide where we want to put it. All right, so when we see BH3, we're going to add it to that least substituted carbon without rearrangement. When we see mercury, we're going to add it to the more substituted carbon without rearrangement. All right, let's try the next one. So remember, anytime you see H+, that's just the generic symbol for an acid. Right? Sometimes we see an acid as H2SO4, so that would be a good reagent you could pick off the shelf. But when we write H+, just means we need some generic acid. Right? Now, when you see acid and water, we're going to add an OH to our molecule across the double bond, but there does have the chance of rearrangement. So it's going to add to the more substituted. It's going to follow Markovnikov's rule, but we have a chance for rearrangement. So what we want to think is step 1, we would actually create a carbocation here. This would be 1, 2, so it'd be a secondary. So we want to pause and see if we move over to 1 carbon to either side, can we go up in substitution? And we actually can, because we could do a hydride shift. So this hydrogen in green will actually switch places with that carbocation. So one of our intermediates that we would form is that carbocation, and this group would shift over, and we'd actually put the alcohol right off of here. So let's see what that would look like. So we're going to draw our molecule. We lose the double bond, and this is where my alcohol comes off the more substituted. Right? I think if people made a mistake on this one, it probably was you putting the alcohol here. Right? And that's because this is one of those that rearranges, where the carbocation intermediate and this hydrogen that's shown would switch places, and then the water adds into that more substituted carbon. So we get that alcohol here. This one, and this is why these different reagents are nice, because they can put stuff in different places. All right, so let's say, okay, you forgot that, you did this in the lab and you got this as your product, but you said, nope, I really wanted it on that spot, right? I wanted it on that more substituted double bond without rearrangement. So then you could use your mercury reagent. And so it's the exact same reaction. Right? But now we get our alcohol on that more substituted carbon without rearrangement, right? So even though this is a more substituted carbon, we're only comparing these two. So this one is more substituted than the one on the end. All right, one last one. We can actually do this one more time, and just kind of for completeness sake, if we do this with BH3, right? So if we did this reaction with BH3 and sodium hydroxide and peroxide, we get one more complement where we can draw the alcohol in the end. So what I would like to highlight is we have the same starting material, right? Same molecule with the double bond. All of these 3 reactions are putting alcohols on the molecule, but they put it in 3 different spots, right? Acid and water, and so I would almost make a note of this, is that acid and water is always going to go to the more substituted carbon, but with the possibility of rearrangement, right? So it always has that chance of rearrangement. BH3 and sodium hydroxide is always going to go to that least substituted of the double bond, but no rearrangement. Mercury is going to add an alcohol to the more substituted, but no rearrangement. Right? And so that's why you get slightly different products. All of them adding alcohols, but slightly different products.